Now here comes to the second paper, which will be presented by Professor Torskaya and her co-worker. And the title of the paper is The Effect of Friction in Sliding Contact of Layered Viscoelastic Solid. Let's welcome Professor Torskaya.
Thank you very much for just now I want to start from the motivation of this work because really I want to present contact problem solution, but this problem was posed by a real tribological problem. And this problem is that for 2 years we have a project with Perth State University. This problem, this project is having to deal with highly elastic materials, and such materials can be used for medical applications, and for example, for medical applications when friction occurs. And one of the variants of such conjunction is tribological friction contact of ceramic and polymer. And this case is really good in practice because this polymer has high wear resistance, but really it also have some problems in contact. One of the problems is biocompatibility, and the idea of our colleagues from Perth State University was to carbonize the surface, and these carbonized layers can improve biocompatibility and also inhibit calcium deposition, which is very important for medical applications. And what do we have? We have the problem, friction problem with very low sliding velocity. We have very highly elastic and viscoelastic material. And maybe if you can see me, I can demonstrate you such material. And maybe after the presentation. And this carbonized layer is very thin, about 50 nanometers, and it is much more rigid than base material. And we tested this material with carbonized layers and without carbonized layers in friction contact with ceramic ball, and we have such results. We can see here that carbonized layer improves friction, but in many cases friction coefficient is very high. That's why if we need to compare to solve contact problem, then it is a question: can we neglect? Should we take into account friction in contact problem formulation or not? And it was the main motivation for our contact problem. And another motivation is that really this carbonized layer can be destroyed. Here is the picture of carbonized layer with cracks, but not only with cracks, but also we have here the piece without carbonized layer. Cracks is not a problem really if we have contact of ceramic and polymer material through the layer. But if we have no layer, then we have problems with biocompatibility and some other problems. And so first, can we ignore friction and contact problem formulation or not? And the second, we are interested in structure of this carbonized layer. And here is the contact problem formulation. And we consider smooth slider. And this slider is in contact with two-layered body. And here we include friction as Maton-Coulomb law. And friction is taken into account in the problem formulation. Here is equilibrium condition, and here is the simplest variant of the shape of condenser, but really of the slider, but really the shape may be different, but the slider should be smooth. And we use here the model of linear viscoelastic material with this constituted equation. And also we use here the simplest one with one relaxation and one retardation time, and the following quick kernel. Here K is retardation time, and this is the ratio of one and relaxation time. And then the boundary conditions at the layer substrate interface. You see, if we consider elastic layer and elastic subspace, then it is no problem to consider full contact problem. But in the case of viscoelastic material, if we have viscoelastic material here or here, this problem is very complicated, and just now we cannot solve the problem. And so we introduce here two different kinds of problems. First, if we consider viscoelastic layer and rigid substrate, then we have the following boundary conditions at the interface. And another problem, which is more close to the previous topic, is when we have rigid layer, but it is a rigid plate which can bend, and viscoelastic substrate. Then we should consider the following boundary conditions at the interface. Method of solution is based on boundary element method, and for boundary element method, we should consider another more simple problem. It is loading of a square by uniform load, uniformly distributed load inside a square. This is the bounds of square, and Inside the square, we have normal and tangential loading. And if we consider elastic case, then we have the following solution obtained by Shapira. And this solution depends on a ratio of elastic characteristics of the layer and the substrate, relative layer thickness, and other characteristics, including elastic properties of the layer. And here is the solution. We can present here the normal displacement of the surface. And if we have normal displacement of the surface caused by such type of loading, then we can use this solution as to find influence coefficient and to use iteration procedure to solve contact problem. And for the case, this function is the function for normal load, and this is the function for tangential load. This function is obtained from boundary conditions using double Fourier transform. And for the most simple case, when we have layer, elastic layer and rigid half space, then this it can be presented. It is presented here. It is relatively simple. In many other cases, this formula is much more complicated, and so I will not present this function later. But now we should go to viscoelastic case. And for viscoelastic case, and for this grid kernel, we have the following dependence of normal displacement, not only on mechanical properties and the thickness, but also on rheological properties. This term is taking into account rheological properties. And in the space of double Fourier transforms, it can be solved analytically. And the result is here. And this is the result which was obtained earlier in this paper for normal load. But just now, I will present you the results, analytical results, which were obtained also for normal and tangential load. And this is the relation which can be used to find normal displacements due to such loading and to calculate influence coefficient to solve the contact problem. And here is sorry. Here is a boundary condition and numerical procedure. We solve the equation. We take the surface region, which is greater than the contact region, and after that we solve this matrix equation. And we solve which, and the procedure is used until we'll have zero condition at the boundary. And after the contact problem solution, we can then calculate stresses. And here I should say that if we calculate stresses, then we can calculate for this problem only stresses inside the layer or inside the half space. We can calculate stresses inside rigid bodies, inside the plate or inside rigid half space. But you see, really, stresses depends not only on +1 ratio, not depends on elastic modulus. And that's why we can approximately use such relations with parameter C, which is the ratio of elastic modulus of the layer and the substrate, for calculation stresses inside the layer. This layer is more rigid, but really it is not absolutely rigid. So we use this as approximation. Here is numerical results, non-dimensional parameters, which we use for calculations. And here is the dependence of contact pressures from velocity. And it was obtained for different values of friction coefficient. You see, really, we have almost no dependence of contact pressure on friction. It is not very interesting but predictable result, because for the case of low compressible viscoelastic solids, the same results were obtained not for viscoelastic half space. And here is the dependence on velocity, low velocity and more high velocity. And we have essentially a symmetric contact pressure distribution due to viscoelastic properties. And this symmetry causes the moment of forces. And here, this is the dependence of contact pressure distribution on the thickness of the layer. And you can see here that the thicker is the layer, the larger is the maximum value of contact pressure. It is also predictable, but also it is interesting that asymmetry of contact pressure decrease with the increase of the coating thickness for both velocities. And hysteretic losses for the case of no friction was analyzed, and we can see here that increasing of thickness also leads to decreasing of hysteretic losses. And it is interesting that we can experimentally obtain the same results. And here are the results of tribological testing when we use a special procedure to neglect friction, boundary friction. And we can see here that increasing of thickness, here is the lowest thickness, here is the highest thickness, leads to the decrease of friction coefficient, which is mostly caused by hysteretic losses. And here are surface normal stresses. Surface normal stresses were used also to evaluate the accuracy of calculations for rigid plate, absolutely rigid plate, and for rigid plate with elastic properties, elastic modulus 100 greater than elastic modulus of the half space. And the effect of friction is most obvious for the case of tensile compressive stresses, which cause the coating fracture. And here are the results for different layer thickness. And we can see here that if we increase the layer thickness, then we increase also maximum value of contact pressure. But it is not the same for maximum values of compressive, which is positive, and tensile, which is negative pressures at the surface. And here curves 1 were obtained for 0.4 friction coefficient, and for curve 2 for 1.0 friction coefficient. And for any case, we have largest value of tensile stresses for the case of thin quarters, for thin hard layers. It is very interesting result. But another interesting result is how these stresses distributed inside the layer. For the case of relatively thick coating, we have here compression, and here we have tension. Here the sliding direction is from left to right. And for the case of relatively thick coatings, the picture is almost the same as for the case of elastic materials. But for the case of thin coatings, we have another picture. We have maximal values of tension at the layer substrate interface under the zone of maximal compression at the surface. So if we have crack, then we have the probability that crack will propagate from the surface to interface, not by this way normally, but with some angle. And such types of cracks are more dangerous because it can cause coating elimination. And I think that it is all for today. And this problem will be analyzed more and more. And the special interest is to analyze for the conditions of polymer materials. But just now we have no real elastic and rheological properties of this material for the calculation. Thank you for your attention.
Thank you, Professor Torskaya. Is there any question?
Okay, my question is, it's the last slide. You showed, noticed that the friction coefficient was equal to 1. Why so big friction coefficient you choose for calculation?
This friction coefficient is real for the case of frictional contact of this our.
What material?
Ceramic.
I didn't hear. I'm sorry.
For polymer material and ceramic. In the second slide, maybe.
No, the last slide, this slide, and friction coefficient is equal to 1. What kind of indenter was used in the tests?
You see, I should go to the second slide of my presentation.
Okay.
Sorry. This one. Here is the table with friction coefficient in contact of a polymer material with a ceramic ball. You can see here that 1 is not large, it is small friction coefficient.
Okay, but in your calculations, you used what kind of friction coefficient for So in calculations, you took 1, but
For this, no. We consider different values of frictional coefficient.
mhm.
For example, here, sorry. Here we have two values of frictional coefficient, 0.4 and 1. But also we have other results for other values of frictional coefficient.
Okay, but at the interface, if the coefficient of friction will be less, what happens at the interface? For 0.4, did you calculate at the interface?
Yes, certainly we calculated in the interface, but it is almost the same as we have for elastic loading, only taking into account that we have non-symmetric pressure distribution. Not very interesting result. Sorry, but it is no such results here.
Okay, thank you.
Thank you very much, Professor Torskaya. A very good presentation.